Hello, everyone. Okay. Thanks, Wenbin, for the invitation and give me the opportunity to present our recent work and discuss with everybody here. Okay. Today, I'm talking about probing the ultra-dense gluonic matter by UPCs at CMS. So during the journey of exploring the fundamental structure of matter, people eventually learned that all the matter around us actually includes our human body are all made of nuclear matter. So the nuclears are made of nucleons, including protons and neutrons, while the protons and neutrons can be further divided into quarks. Under the normal conditions, quarks are confined within the nucleons by the strong force, which are mediated by the gluons. Since they are always confined, so how do we learn the inner structure of these nucleons? So the idea is very simple and actually also very brutal. We just smash them with the high energy probes. For example, we can accelerate electrons to high energy and let them penetrate deeply into the proton. And these electrons can be scattered off one of the proton's constituents. By analyzing the outcomes of these deep inelastic scatterings, we can learn the proton structure in detail. So what do we found? Right? When we probing the proton at the low energy, so the observed patterns are mainly 3 valence quarks and a small amount of gluons. However, if we increase the probing energy, we probing the lower X region, we basically only see the gluons or see the C quark and any quark splitted from those gluons. If we keep increasing the probing energy, we will just see more and more gluons. The right figure shows an example of the parton distribution functions extracted from the electron proton collisions at higher. As we can see, at the relative higher X region, the valence quark dominant. While go to the smaller and the smaller X region, the gluons keep dominant and keep increasing. So a natural question we want to ask is that, what is the fate of gluons at the extreme density towards the unitary limit? If we let the gluon PDF grow without any control, it will violate the unitarity of the QCD. So there must be some new mechanisms to stop such a rapid growth behavior of the gluons at some point. So while the growth of gluon densities are explained by the splitting of the soft gluons, on the other hand, we know the two gluons can also recombine into one gluon. So such a recombination probability actually has a nonlinear dependence on the number of gluons. So at sufficient lower X region, the gluon recombination is expected to balance the gluon splitting, which would eventually saturate the gluon density and form a new form of matter, the so-called color glass condensate. However, the exact condition to realize or observe the gluon saturation is still not very clear today. The search of the gluon saturation has been one of the main physics motivations for the construction of the future electron-ion collider. But today, I'm going to introduce how to make use of ultraperipheral collisions in existing heavy-ion collisions to explore the gluons at the extreme dense region and search for the gluon saturation before the operation of the EIC. In the ultraperipheral collisions normally referred to as UPC, as we already heard about the UPC. It is about the collisions actually happens between two heavy ions at a distance larger than the sum of their radius. the electromagnetic field around the relativistic ions can be viewed or can be equivalented as the flux of quasi-real photons. And these photons from one ion can interact with the photon from the other ion, or directly interact with the other ion nucleus itself. In this sense, the heavy ion collider can also serve as the photon-photon and the photon-ion collider. Among many interesting physics processes of the UPCs, the vector meson photon production, especially the heavy vector meson photon production, is of particular interest, as its production cross-section is predicted to be very sensitive to the gluonic structure of the nucleus or nucleons. So the vector meson can be produced while the coherent production and the incoherent production, while the coherent production is about the photon fluctuated dipole or the QQ pair interact with the entire nucleus as a whole. And the incoherent production is about the photon fluctuated dipole interact with the individual nucleons, while the coherent production usually, after the interaction, the target nucleus remain intact, and the resulted or the produced vector meson usually has very low PT, about a few tenths of MeV. And in this process is probed the average gluon density among the entire nucleus, while the incoherent, after the interaction, the target nucleus usually breaks, and the produced vector meson usually has a few hundreds MeV PT. And if the nucleus actually, the nucleons got a break, so that means this process probably even smaller scale inside the individual nucleons. It can actually produce the vector meson about 1 GeV. So in this case, it's probing the local gluon density and the local fluctuations. Once we measured the rapidity of the produced vector meson, we can then know the associated photon energy and the associated interacting gluon X and the center mass energy. The gypside photoproduction via the gamma proton interactions have been investigated and studied in very detail at both HARO and the HC, as we can see from this result. The result from the HC, including the ALICE and the HCB, together with HARO data, follow a common power law trend. And this trend holds from about 20 GeV to almost or just about 1 TeV. This is consistent with the expectation that the gluon density just keep rapidly increasing inside the proton, while the proton is a free nucleon. So inside a free nucleon, even the data goes down to X region about 10 to -5. There is no clear indication of gluon saturation yet. So while the search of the gluon saturation in a proton or a free nucleon is so difficult, the natural idea is to look at those objects which has much higher gluon densities. So the gluon densities inside the nucleus is enhanced by a factor A to the power 1/3. Thus, the saturation scale can be pushed to be at a much higher region. So what does it mean? It means it allows the gluon saturation can be reached at a relatively much higher X region. As the directly increase of X values in the experiment requires the increasing the probing energy, which is very difficult and expensive. So the search of gluon saturation inside the nuclei will be much easier and low cost compared to the free nucleons. So the gluon acceleration search in the photon-nuclear interactions has been made or has been performed with very good precision via the coherent GPCI photoproduction in lead at actually as shown in the right figure. So while the data itself shows strong suppression when compared to the theoretical curve, which ignores all the nuclear effects, no any gluon acceleration effect, no the so-called gluon nuclear shattering effect. However, the rapidity distribution of this data from the high rapidity to the middle rapidity is still a puzzle for theoretical studies. As we can see, all these models considering, no matter it's considering the gluon acceleration or the shattering effect, either miss the high rapidity or miss the middle rapidity data. None of these models can describe the entire rapidity distribution. So actually, each data shown in this figure includes the contributions from the both small x gluons interactions and the high x gluon interactions. For example, if we look at the rapidity around 4, it includes the contribution from x around 10 to minus 5 and also from x around 10 to minus 2. Well, the later actually contribute about 95%. So the small x contributions will be actually buried in the high x contributions. So this is mainly due to the so-called two-way ambiguity. Okay, please allow me introduce more about the two-way ambiguity in the next slide. The two-way ambiguity in the experimental data is mainly due to the symmetric nucleus collision, nucleus UPCs. The measured GPCI at a given rapidity can be produced via a lower energy photon interacting with a higher X gluons of the target nucleus. In this case, the GPCI will go with the target nucleus going direction. On the other hand, the measured GPCI can also be produced via a higher energy photons interacting with the lower X gluons. The produced GPCI will go with the same direction with the photon emitter nucleus. The single measurement at one given rapidity does not allow solving the equation. This is the d sigma dy is actually what we measure. This is the inclusive or total cross-section, which contain both contributions and the associated photon flux. So we always measure the sum result. So one single measurement does not allow solve the equation. The theoretical paper published in about 10 years ago proposed a novel approach to solve this two-way ambiguity while looking at the forward-emitting neutrons. The basic idea is that when two ions interact at a small impact parameter, the additional soft photon exchange will result in more neutron emissions. We can make use of these neutron emissions to control or to know the impact parameter for the coherent GPCI production in the UPC. And in this case, it's actually similar to the centrality in the hadronic ion-ion collision. So if we have more neutron emissions, for example, the xn means the xn means larger or equal to 1. If for xn, it has the smaller impact parameter, and then 0 and xn, that means only one side has the neutron emission, and then 0 and 0 means actually no neutron emission, right? So then we actually can construct more than one equation. In that case, we can solve the equation to get to disentangle the low photon energy contributions and the high energy photon contributions. Here we show an event display of the typical UPC event with only 2 muon tracks reconstructed in the CMS tracker and the muon chamber. And after we successfully identified the muons, we can reconstruct the muon event mass and the PD distribution. The signal yield of the coherent GPSI can be extracted by fitting the mass and the transverse momentum spectra. And after we extract the raw yield, we can then apply the efficiency, acceptance corrections, and the fade down and the incoherent corrections. Finally, we can measure the cross section. So here we show the red point as CMS data. As we can see, the CMS data, if we plot with the previous published data from ALICE and the RCB, we can see CMS data cover a unical repeated region, and CMS data follows the ALICE for the repeated data very nicely. And we can also see there seems to be a tension between the CMS and ALICE for the rapidity data and with the ALICE middle rapidity data. So again, there is no any theoretical calculations which can describe the entire data trend from the high rapidity to the middle rapidity data. The curves, theoretical curves, either miss the high rapidity or miss the middle rapidity data. So there is a puzzle. So what we should do? So a deeper look of the GPSI photoproduction from a single gamma lead interaction and without the two-way ambiguity will actually tell us more. So that is what we can do. So while the GPSI is reconstructed by the central detector, the CMS main detector system, the average impact parameter are controlled by the forward neutrons measured by the ZDCs. So here, the ZDC is located at about 40 meters away from the interaction point in each side of the CMS system. And the bottom left shows the neutron signals detected by the CMS ZDCs, and which will help us to classify the interested event into 0 and 0 and 0 axon and the axon neutron class. And then with that, we can measure the cross section, the total cross section, inclusive cross section, in different neutron class, as we can see in this figure. So again, actually, no any single model can describe the data from different neutron class. And the most important thing for this measurement is to allow the low energy and the high energy photon-nuclear contributions of single gamma lead interactions for each given rapidity. So before we see the results from CMS, we can say before the publication of our measurement, we calculate the approximated data from ALICE and RCB at the highest rapidity region, and the rapidity equals to 0 region, because in this two regions, the two-way ambiguity can be ignored. So as we can see, the ALICE and RCB data is very close to the theoretical curve without the nuclear effect at the low W region, the low energy region. And at the about 125 GeV, the data shows strong suppression compared to the this curve. And if we put on the CMS new data, which is after disentangle the 2-egg mutate, we can see that at the low W region, CMS data continues the trend of the existing data, shows rapid increase at the W lower than 40 GeV. And then when it goes above 40 GeV, the data shows much slower, nearly flat trend towards even towards 400 GeV. And no any model actually can describe this observed trend for the entire W region from about 20 GeV to 400 GeV. And if we calculate the nuclear suppression factor, which is defined by the square root of the experimental measured cross-section over the impulse approximation curve prediction. The impulse approximation is actually just directly integral the total coherent contribution from individual nucleons without considering any additional nuclear effects. The approximation is actually just this curve. So that means we take the ratio of our measured data to this curve and then take the square root. Because the cross-section is proportional to the square of the gluon density. So after take the square root, this ratio actually can tell us the nuclear gluon suppression factor. As we can see, at the high X region, all the data actually shows nearly flat from the low energy, from the higher X to the relatively the intermediate X region. And then when we go to the lower X region, below this data point, we can say the data shows quickly decrease towards 10 to minus 4, 10 to minus 5 region. So this trend actually beyond any model expectation. So what is the physics, underlying physics behind? So if the reason for this observed data trend is really due to the splitting and the recombination of gluons becomes equal, so this could set as clear evidence of the gluon saturation. However, we also notice that if another theoretical paper also pointed out, if the target nucleus becomes completely absorptive to the incoming photons at the high energy, once the gluon density is high enough, the photon nucleus interaction, the cross-section itself can saturate. The target nucleus can become as a black disk that would also saturate the cross-section itself. So, and another interesting conclusion from this black disk limit is that once the nucleus becomes completely black disk, the internal structure will be invisible. So that means in the future, if we can measure the incoherent production cross-section to this high energy, that will be very interesting, because if this is really due to the this reason, the internal structure become invisible, the incoherent production should be should disappear. So in the future, we're gonna measure various vector mesons in different nucleus UPC equations with the neutron taggings. We're gonna measure the coherent production, incoherent production together, and we also want to make use of different mass of the vector mesons to control the double size and also the hard skills. We're gonna also explore the different nucleus to explore the A dependence and vary the saturation scales for the search evidence of the gluon saturation. So for the summary of today's talk, so first time we actually realized the disentangled the low and the high energy photon contributions to the coherent gypside photoproduction. And we successfully measured the coherent gypside production at new low X gluon regime. The X corresponding to 10 to -4 to 10 to -5 region in the lead nucleus. And the cross-section with the energy is not predicted by state-of-art models. So the underlying physics is still not very clear. So we will need theoretical studies to help us to figure out this measured result. And we also, from the experimental side, we will also try to measure, to provide more measurements to help figure out the underlying physics. So in the future, the high lumen HC, including the CMS phase 2 upgrade, we're gonna bring new exciting opportunities for many measurements. Okay, thank you.
Okay, thanks for Dr. Chen. We have half hour for discussion. It's time for questions. We can read. Okay. Spencer, yeah.
Thanks. Very nice talk, Xiaoqian. I have a question about the results, like is in this figure 34 with this surprisingly flat cross-section. How did you account for uncertainties in the probability of having additional photon exchange, to give you the excitation? Is it possible those uncertainties are underestimated, which could tilt the shape of the curve?
I think so you are actually talking about the photon flux uncertainty, right, Spencer?
The photon flux, if you produce a J psi that takes one photon, I'm talking about the additional photon flux to excite one of the nuclei to get 0n xn or xn, and that depends on a bunch of theoretical inputs. But how do you account for the uncertainty and sort of the data that goes into those probabilities, like the curve plot on the right? And how do you know that, that those uncertainties are not underestimated? Because a lot of it is based on, in some cases, 50-year-old data, which has been compiled and processed.
Okay, that's a very good question, and also crucial for this measurement. So firstly, the additional photon exchange itself is always, as you know, is the soft photons, right? Only about 10th MeV can excite and introduce the electromagnetic dissociation, right? And such a cross-section is huge. It's about 200 bar, right? Whereas the gypside production cross-section itself is only a tenth of millibar, right? It's about a factor of 10,000 times higher for the EM dissociation neutron emission. So that means the impact parameter control from this EM dissociation is actually does not depend on the gypside production cross-section itself, right? So this is actually makes the physics process of the EM dissociation neutrons and the gypside coherent gypside production itself are actually independent. So this is the first point. And the second point is that for the photon flux calculation, so the uncertainties can come from the knowledge from the nuclear radius, right? And the skin spread, skin depth, and also come from the uncertainty from the the photon-neutron absorption cross sections, which actually come from the experimental data, right, as you mentioned, and all these uncertainties are taken into account for our systematic uncertainty calculations. As you can see, that is why after the disentangle, we actually have this box. This is actually the dominant uncertainty from the photon flux calculation. Yeah, hope I answered your question.
So what did you assume for the uncertainty on the gamma A going to A star cross section?
That assumption is actually come from your paper, right? What the starlight actually used from the previous measurement. I don't remember. It's the PIE paper, right?
Yeah, the
5.5 uncertainty. Yeah,
right.
That actually is huge uncertainty.
I sometimes wonder if the uncertainties in that paper are maybe underestimated.
Okay. Yeah, if we get the updated uncertainty on that part, we can actually update this disentanglement, because in the published paper we also published the cross section without disentangle, right? We can always resolve the disentangled result in the future, right?
Okay, next question from please.
Okay. Thank you very much. Very nice talk. And I have a similar comment as what Spencer said. I think the theoretic uncertainty in this decomposition or what the extraction of the photon-nuclear collision maybe, I think, to my view, I think is definitely underestimated. So in the sense that your cross-section estimate from this for this process is I don't know. I mean, there's a large uncertainty there, and we actually don't know. Maybe in the end, we don't know, and we don't know yet the physics behind this, how you can separate different terms. So a related comment, for example, if you really kind of trying to say this is coming from gluon shadowing, right? So you would have seen this already in other process as well. For example, this tremendous data for the PA collision at a similar energy or X range at LHC, right? But you haven't seen anything, right? Like a heavy flavor product in PA collision, which definitely probes the ground distribution there. And if your argument about the black disk limit, so that means all the current LHC collision data have to be reanalyzed, right? So that means this a whole bunch of consequences will come from that. And I think we have to be more careful about this statement and conclusion from this measurement. It's very complicated how you, because you basically from AA NACO you mentioned and in your presentation, and also Spencer comments how you get AA goes to GIPSI and separate that from the photon flux and the photon nucleus collision. It's not clear, I think, at this moment.
I agree. It's not that clear, but the disentanglement itself, I have to agree. We have to rely on the best method we can make use at today, right? Yeah. If we have better control on the
there's no doubt. The experiment, I think, but I really. I think we have to keep in mind the interpretation of the what.
The black disk limit, actually, I contacted the author from these two papers. They actually brought out the black disk limit from their current framework. The GIPSI double size is too small to reach the black disk limit, because the black disk limit does not only depends on the target, it also depends on the incoming dipoles. So the dipole size is too small to reach this. But they don't have a good explanation on the observed trend at this moment. We actually write down the Bradley limit here just phenomenologically. It's actually can give us the much slower increase in trend in the cross section. It's not a conclusion. It's just a question or a guess. In the future, we're gonna provide the for example, the incoherent production as function of W, right? It can tell us whether it actually forbids or strongly suppress the incoherent production due to the suppress of the internal structure.
Can you also go back to 34?
Okay.
Yeah, here is fine. So you see that the right plot, you have basically you don't have data for 10 to minus 2, right?
10 to minus 2?
Yeah.
There is a gap
Yes.
here. Yeah,
So,
but
so if I believe what you said, if I believe the interpretation of the result, you would be able to see the so-called anti-shadowing. So that's around the 10 to minus 2 or 10 to minus 1. So you would say the ratio of this ratio actually will be above 1. So
yeah,
you can say the you will definitely see the shadowing, but also you see the anti-shadowing.
yeah.
Right?
However, the current difficulty is that the anti-shadowing is actually not happens around this region. Around
Where
here.
it happens?
I think it's
Is there?
yeah, some region here, I think. But I don't remember the exact place. All here. But
No. Definitely
yeah,
above
all
10 to
here,
minus
yeah.
2.
Yeah. Well, during the discussion with Vadim and Michael, they actually try to think about this direction to aid the anti-shadowing contribution in their current shadowing model. But we never get updates from them in the past 1 year.
Okay.
Yeah.
Thank you.
The main difficulty is that the X region is different.
Mm-hmm.
Yeah.
Okay. May I have a question? Could you turn to page 15? Hello? Yeah. I just want to ask why you don't consider the interference contribution. I mean, in our calculation or STEM estimate, at least at the middle rapidity, there is 20% effect from the interference.
Yeah, that's a good question. Actually, from the physics picture here, it's also very similar between this. The main difference that the interference is actually is mainly due to when the rapidity close to 0, the two photons actually have almost the same energy. You cannot distinguish the photon emitter and the gluon emitter, right? Actually, the interference effect is more significant, not only for the low rapidity, but also requires the low PT, right? For the, maybe lower than 10 MeV, it's very close to 0. So that actually that is the requirement. For our analysis, it's about the average rapidity around 2. So in this case, the interference can be safely ignored.
But if you want to compare to Alice measurement from at a middle rapidity, then Alice data, the interference should be effect.
The Alice data should have the interference contribution. But from the theoretical calculation, I think the interference contribution, this is the PT integral cross-section, right? The interference mainly modify the PT shape. It will actually has the destructive contribution in the very low PT region, and actually it will actually change the PT shape in the it will enhance a little bit in the high PT region. Right? If you integrate the total cross section does not change that much, so that is why it does not actually affect.
Okay. Yeah, I have another question. Can you mix the gamma P in the UPC, like gamma lead, the UPC in the gamma lead collision? I mean, lead emit photon collide with proton.
You mean this? If from
Yeah,
the P-lead UPC, we can actually measure it as what Alice did.
Okay, so
Yeah,
you can.
that will be dominantly by the photon emitted from the lead because the Z is too large, right? So the photons from the lead will dominate the gypside production. The photon interact with the proton. So the final measured cross section will be photon interact with the free proton.
Okay.
Yeah.
Thank you. Okay. Do you have more questions? Okay. If no more, we have a question from Min Jun, please.
Thanks for the nice presentation. I have kind of practical question on your slide 33, which you show the future opportunity. So I think you show the big table, the list of the table, which can be measured.
Oh,
Here.
that is.
Yeah, one before
yeah.
right here. Is it for which runs 3 data, or is it including?
Oh, this is from the Sun Yellow report. This is the future our goal. This is actually based on the simulation which can actually fly into the projected detector acceptance. It's projected.
Okay, for the but in which kind of time window you anyway you have to collect the data, right?
Yeah, that will be the after the long shutdown, and with the RES 3 we already have some data.
Okay, I see.
Yeah. In the RES 3, the ladder UPC we collected about the similar luminosity as the REM 2.
Okay.
Yeah.
I see. Thank you.
And at the end of this year we're gonna take more data.
Right, but still it's not feasible to go down for the upsilon production, right?
The upsilon production, in principle, we can produce the upsilon, but as you know, the main difficulty is at the upsilon region because the reduction of the vector meson production is significant, whereas the underlying background from the gamma to dielectron is very high. So the signal to background ratio is not very good. So that is a challenge there.
Okay, so it can be only done by subtracting based on the model calculation or the simulation of the gamma to dielectron, or is there any kind of discriminating observable which you can use for separating the signal in the background?
For that one, we have I did not directly work on this, but as I can imagine, we have to make use of the environmental mass distribution itself because the dimuon distribution is generally smoothly and flat, and the upsilon has the peak.
Yep.
But as you know, it's still the challenge is there, as I can imagine.
Yeah. Thank you.
Okay. Do you have more questions? Okay, if no more questions, let's thank Dr. again.
Okay.
Okay,
Thank you.
thanks for joining.
Thank you, Dr.